So this is project two for fluid mechanics with Ozbay. Um, Today I'm going to do the Fluent 2D flow simulation of airflow over a flat plate. It's for laminar flow, and yeah, these are just the instructions. And for this, for my team, I'm doing part one, which is get the velocity and pressure contours around the flat plate, and B, uh, plot the velocity profile. Okay, to begin, I'm gonna open up the workbench, just right here. So first things first, I'm gonna get fluid flow fluid into the workbench right here. Um, okay, I just figured out how to get thing on the side over here. All you need to do is go view and then properties, uh, view properties, and just check it. And then you change this to a 2D analysis. So then that's why we needed to put the properties on. So let's do that real quick. Here you go, 2D analysis. Now we're going to go over here, right click, and then press new design modeler geometry. Wait for it to load. And now we go into the XY after, since we're doing a 2D flow. You have to do it in the Y and the X axis. So you have to click on the Z to get it look like this. And then now you click on now XY plane. Go to sketching. Now let's just create a little rectangle here. It doesn't really matter how big you draw it because we'll be defining it later. But you do need to start from the really center. Make sure you get the center like that. Okay, let's go do some dimensions right here. General. In the assignment right here, it says we needed to length is equal to 100 centimeters. So that is 1 meter. So we just simply just get the horizontal on both ends, right? Like that. And then get a for 1 meter for the length of the rectangle. Okay, now we do the height. It doesn't really matter what the height is because in here it doesn't specify. But for my purposes, I'll just do 10 centimeters, which is like 10 centimeters, which is 0.1 meters. There we go. Right now, this whole thing is fully defined, which is good. Now we go to concept and then concept. Right now we, no, then now we go to concept and then surface from sketches. Click over here, click sketch one, and then apply. So now we have, now it's blue, and then we generate. So now it's filled in right now with the gray color. This is kind of like our testing area. Okay, now we have our geometry done. We go back to the workbench, and now it should update. Yeah, as you can see a check mark, but let's just make sure real quick. Update to make sure, and everything should be correct. Since we see the green check mark, we can safely close this thing out because we don't need it anymore. Well, we do need it, but like we don't need to work on it anymore. It makes sense. Now, before we forget, let's just save our project before anything happens. You just go right here, and let's just save it to file. Let's just do like do next thing we do is of course do the mesh. You just double click here, just wait for it to load. And now that it is open, you can see our little gray rectangle we made in the geometry right here. Things first, right click this, insert, okay, right click this, first things first, insert, and then face meshing. Our face is indeed selected, as you can see. It is the green little square at the top. Select our geometry, just click, and then apply. Now it's purple. Woo. Now it's generating. We can see our first mesh. It's gonna load. Yeah, just a bunch of squares. We will make more squares in the future, but yeah, this is just the beginning. Now I have like a little grid. This is also two big squares, so that's gonna be like we need like really tiny small squares to see the boundary layers. We need to add more mesh, so to do that, we need to go to mesh, insert, and then sizing. For the geometry, we'll select two edges, so we need to first click this, double click it, and then you click on this one and this one, or you can control, so you can select both, and then you apply, type, should change to number of divisions. For number divisions, let's put like 50. This will make the mesh more finer, if that makes sense. Select the capture curvature to no. Make this behavior a hard behavior. Now we generate. Now we can see our mesh. Um, there is more squares now since we did do that two edges, which is good. There is more details. It is a bit more fine, but we're not there yet. We do need to add more squares so then we can get more better results. And now we need to right click mesh here, insert another sizing mesh. Now this time we're actually just gonna do the leading edge right here and hit apply. We type. We need to do number of divisions again. Now we're doing 60 divisions for the sides here. We zoom in over here. You can see that there is 60 divisions, which are all divided equally. To change it, we need to change capture curvature to no. Um, behavior type is hard. And then for bias type, we are going to change it to the 4, 3, 2, 1, 1, right? To the top one, the top bias. And then the bias factor of 70. Now we have a better separation. It is more defined and more fine at the bottom, and it's less defined at the top, which means that there'll be larger squares at the top and then smaller squares at the bottom because we want more data points at the bottom. Now we hit generate, and then now we can see our little mesh here, which is pretty interesting shape if I have to say so myself. And now we have to do basically the same thing we did over here to over here. So to do that, we right click mesh, insert, sizing, and then click on this side. Apply. number of divisions, 60 divisions again, no capture curvature, make it to hard, bias type is the top one, bias factor, it'll be 60 once again. If you notice, it is in the wrong direction, so we do need to reverse the bias. So let's just hit apply, and then you need to first click on the line, and then you click apply for reverse bias, and now it's in the right. It is more defined at the bottom and less defined at the top. And now we generate. It's generated. Now we can see our mesh. Now it is way more better, and the thing that we want with four different meshes is more defined at the bottom and less defined at the top. And now the next thing, we go back to Workbench, right click and update. So we get the check mark. Since we get the check mark, now our mesh is good to go. Now we can close our outer meshing since we're done. And now we go to setup since we're done. Well, since there is a check mark on mesh and we did close out of the mesh. So double click setup. Make sure you click double precision checkbox. For solver processes, we need two, and then just hit start. At the time it loads, you should be on this screen. You can see the mesh that we did in green. Now I just realized that I forgot a step in the meshing progress. So let's just double click this to get it back. I shouldn't have closed it. Thing I forgot was to name the, the things that we did. This is important because ANSYS actually uses these names to do whatever, to um, understand everything that's supposed to represent. So while our mesh loads here, um, what you do is pretty simple. You need to go over to the edges again. Just click this wall here, click N on your keyboard. This is called the inlet, not selection. Select this wall, click N. This will be the outlet. This surface here, click N. This will be our plate, which is the bottom plate. Oh my gosh, I spelled it wrong. The plate. This top surface should be, we'll call it the far field. This is basically far away from everything that's happening. Now you can see when you open this, you can see all the names we have, the inlet, the outlet, plate, and then the far field. And don't forget the face. That was the first mesh we did. We're just going to name it airflow. Mesh, good, generate, update. I can go back on our mesh, update it here again, just to make sure. We do have the green check mark. Let's close this out. Since we did mess up, we do need to exit out this again. So exit both. And then we need to open up the setup. Now we do have our incoming arrows. After you click on setup, before it didn't have that, now it does, which is exactly what we need. First, we need to make this a laminar flow. So to do that, we need to go to models here and then viscous. Change this viscous to laminar right here. Now it's change to laminar. Look in general, it is pressure-based, absolute, steady, and planar, which is all good. Going to materials, fluid. in air. And the directions, it says our air needs to be 1.2. As you can see right here. It also says the viscosity of air is to be 1.8 times 10 to the negative 5. So let's do that real quick. Let's change the viscosity. Let's change that to 1.8. Change. Now we save it by closing. You can check it by clicking on this again. Perfect. Now we do boundary conditions. Right here. Our inlet here. Lumpy inlet. We get this thing right here. Velocity magnitude should be 2 meters per second. Now we hit apply, close. If you click on this, you do see the velocity magnitude. Now we have to check the actual plate here. It's showing type wall, which is good. You can open it up by double clicking. No flip, stationary. Nothing changed. Apply, closed. Now we go to far field here. Change this wall to type symmetry. Apply, close. Now we have all of our boundary conditions set up. All right, with the methods. First, we change the setting from coupled to simple. Click over to right over here. There's initialization. Click on standard initialization. We need to compute from the inlet velocity. It should be 2 in the x direction and actually 0 in the y direction. Now I go to monitors, go to residuals. We're just making it more precise, so add 2 zeros to each. Okay. Now we're just gonna hit initialize right here. And we're all done. Now we're all initialized. Now let's run the calculations. For number of iterations. Should be 10,000 iterations. Now we calculate. It'll make a little nice chart. Okay. Now that the calibration is complete, now we can see the scale residuals. Here's our graph. For the project, let's see, we need for A, we need to get the velocity with vectors and pressure contours around the flat plate. It does say with vector. To go do that, we need to go to results, graphics, contours. Here it is. This is our velocity contour. These are all checked. Contours of velocity, velocity magnitude, save display. Now we see our nice contour, as you can see. It is super small over here, and it gets more big as you move uh, to the right. Now we need to do add the vectors on this contour. So to do that, wait, you zoom in over here. Vectors. This is velocity vector. Global range scale. Vectors of velocity, colored by velocity, velocity magnitude, and save. Now we have the arrows. Now it turns the boundary layers into this whole thing. Now you can see the arrows going up and it gets bigger and more more dense at the bottom, and then big and less dense at the top. To combine these together, I'm going to go to scenes here, name it velocity, title velocity, velocity scene, because this can have an error. Given display. Now it is kind of hard to see, so we do need to add transparency. Let's put it to like 68 or something. It doesn't really matter. Now we do see the whole both things combined with the arrows. Actually, let's just put it to 60, make it look better. This is basically a copy of this, so we just need one of them. So we can just exit out one. Next contours we need will be all of our pressure contours. Do that. We go to contours. Now it's a pressure. So after we get the velocity contours, now we need to get the static, the dynamic, and the static save display. This is our static contour. Take a screenshot. Now we get do the dynamic pressure and screenshot it. Here's our dynamic. And then our total pressure. And then here's our total pressure. Next up for the project, we need to plot the velocity profile at these two places. What we need to do is go into surfaces, 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 so exit out, surfaces, new, line slash right. There you go. We're gonna call this surface x35 because that's our centimeters. All right, let me check. Yes, we need to do a velocity profile at 35 and 75 centimeters. So let's just go over here, 0.35, our height is 0.1, in our case, 0.35 for x12. Okay, now we need another surface here, it's 0.75, change this to 75, change this to 75. Now we have both of our surfaces. Now we go into our XY plots right here. This is basically going to be our velocity profile. Hit control, get these two selected. For points, don't write the file yet so that we can actually see the graph first before we export it. Now positioning on the x-axis, y-axis function should be velocity, x-axis should be the function of mesh. I'm going to save and plot. Oh, I did that wrong. We need to put a y coordinate instead of x coordinate here. And then it should look good. There we go. Here's our plot. Now you can see the different velocities right here as we go up into our y coordinate. The velocity magnitude increases until it stops abruptly at 2.1 for the purple line and then 2.07 for the blue line. To write it to file, let's go here, click it on the right. Yeah, and that's basically it for my part. Let's switch it to my next teammate, which they will do part C, which is to plot the wall shear stress and friction coefficient in Excel and to get the drag coefficient using the Fluent. So I'm going to pass it on to him.
Hello, this is Nevin. I'm gonna be doing part C, and this is our setup right here right now. So let's go. So we're gonna go to our XY plot under plots. The results. Yep, one new. One. First one is on. We're gonna do wall flexes. Hold up. Y-axis. Yep. Let me set it as plate. Yep. Then we say plot. Then you'll see this. Let's go back to the one we just did. Edit it. Let's change it into skin friction coefficient. Okay. All right. Yep. And this is part C done right now. And we would be comparing with our theoretical ones with the same graph for both as well. So give us a second. And I think we should be done by now. Yep, we're good to go.
Hello, my name is Stanley. I'm going to be doing the part B section of this. First thing we're going to do is go to reference values and change the density to 1.2. And the viscosity also to definitions. Yeah, bro, I've done nothing, bro. It's literally just
No playing Minecraft.
I
Work
click
on the Excel sheet, bro.
ignore my laugh. All right, lucky. After computing, I'm good. Ignore my partner, bro. They're fucking retarded. Alright, lucky. After computing, I'm good. Ignore my partner, bro. They're fucking retarded.
Hello, my name is Khang Fan. So here's our Excel sheet. I'm just gonna explain my part, and then my two other partners will explain theirs. So for me, I had to do part A and part B. So for here, wait, is this actually screen share here? Yeah. Um, I did the velocity profile for meters per second times versus the y coordinate. So here, you for the assignment you had to do it for 0.35 meters and 0.75 meters. So that's the two data points over here, data tables right here, and then that's how I got this graph here. I also had to do the velocity with vector and pressure contours around the flat plate, and that's the chart you see there. Oh my gosh. Please. That's the chart you see here for static pressure, dynamic pressure, and total pressure. And then here is the velocity magnitude with the arrows for the vectors, with the velocity vectors. And oh my gosh, bro. And then here is the graph that I got from ANSYS, which is the velocity magnitude versus the y coordinate right here in ANSYS. So that is my part done and explained. I'll switch it to Nevin, who did part C.
Okay, so this is Nevin. For part C, what I did was pretty much I set my XY plots and basically set the settings to either shear wall stress or the slim skin friction coefficient. Then after I imported the values into what we call an Excel sheet, I use these what we call formulas here. So I use a boundary, no, actually, I use the wall shear stress formula and I use a local skin friction for, coefficient to get these values over here. So basically to find these values, I basically yeah, I use these values to find the what do you call it, the total answer. Then for the graphs, I pretty much use the y value, the theoretical wall stress, and the shear wall stress. And the same thing with the skin friction. I basically use a y value, shear the skin friction coefficient, and theoretical skin friction coefficient. And this is the two graphs I got right here. So you got this is a slim wall, and we have the slim skin coefficient right here as well. Zoom it out so you can see. There we go. All right, these two. And that's all it for me. It's pretty much a short part for me. So the next one will be Stanley Jong.
Right. For my part, I did the drag coefficient, which is right here. Oh, okay. No. Dude, why does it zoom so much, bro? All right, for the drag coefficient formula, I used the CD, which is the 1.328 over. For L, we use like 0.35, 0.75, which is right here. When we're doing oh, my bad, over here. So this is the drag coefficient. And then here's the theoretical and the error. But for this part of the BLT, if you can tell right over here, we use the formula given, which is right here for boundary layer thickness. This is something I did as well for Khang's part, but here's the drag coefficient formula I use for the over here. Yeah.